Hi guys, so today we're going to be doing Chemistry 9701, paper 52, October-November 2022. So this is just a scanned version of the paper that I've done. So number 1, eggshells contain a high percentage by mass of calcium carbonate CaCO3. A student wants to find out what percentage of an eggshell is calcium carbonate and uses the following method. This method uses a known excess of acid, like HCl, to dissolve the eggshell. The amount of unreacted acid is then determined by titration with an alkali. So there are 2 steps to this. Then assume the acid only reacts with CaCO3 in the eggshell and nothing else. So step 1, wash an empty eggshell with distilled water. Then warm the eggshell in an oven for a few minutes until dry. This is so that there's no water left and it's only going to be the mass of the eggshell left over. Then step 3, grind the eggshell into a powder. Usually when there's a step like this, grind something into a powder, there's usually a question relating to surface area, which we will see in this paper. Then step 4, weigh approximately 2 grams of the eggshell powder into a conical flask using a balance which measures to 3 decimal places. This 3 decimal places is going to be used in a later question. Then step 5, add 100 cm cube of 2 mole per dm cube hydrochloric acid to the conical flask. Then loosely cover the conical flask and leave for 2 days. This is to make sure that the reaction have been completed. So this is the first reaction. Then filter the contents of the conical flask with any rinsings into a 250 cm cube volumetric flask and top up to the mark using distilled water. Then transfer 25 cm cube of the solution prepared in step 7 into a conical flask. Add a few drops of Theno blue indicator and titrate against 1 mole per dm cube sodium hydroxide using 50 cm cube urate. So this is the second step, yeah. The first step is this. The second step is titration, this. So titration in here, the one that's gonna be in the burette is going to be NaOH. The ones that's going to be in the flask is going to be the solution. The solution consists of what? It consists of 25 cm cube of the previous 250 cm cube volume of unreacted HCl. So the concept of this is quite hard to grasp, so I'm going to be saying it in easier words. So first, the CaCO3 powder is going to react with excess of HCl. So for example, I can say there is 100 units of HCl added to a container with CaCO3. Then they react, but not all the HCl react with the CaCO3. For example, only 25 units of the HCl actually reacts with CaCO3 to form this, okay? So actually only 25 units react to form this and 75 units HCl is unreacted. Then this 75 units of HCl that is unreacted is transferred to a volumetric flask and filled in up to 250 cm cube right here. So now you have 250 cm cube of unreacted HCl. Then this unreacted HCl, you want to take 25 cm cube of it. You're gonna take 25 cm cube of it, and then you're gonna react in a titration reaction with NaOH. Okay, let's continue first, then let's go back later. So let's start with the questions. AI, suggest how the student could confirm the eggshell is completely dry in step 2. By step 2, warm the eggshell in an oven for a few minutes until dry. So by warming it, you can reheat and you reweigh the eggshell until it shows that there is a constant mass and there is no more water that is evaporating. So there is no more water in the container. So just answer reweigh until it shows constant mass. State why the eggshell is made into a powder in step 3 before making up the solution. Explain your answer. See, like I said just now, there will be a question related to powder and surface area. So eggshell powder has higher surface area than uncrushed eggshell. So this higher surface area increases the rate of reaction. I suggests why the solution is left for 2 days in step 6 before being used. So step 6, it says that the eggshell powder is placed into a conical flask, then the HCl is added to the conical flask, then you leave for 2 days. So this reaction is left to react with each other for 2 days, so that to ensure that the reaction is complete and or all reactants have reacted fully. So for B, the student uses exactly 2.136 grams of powdered eggshell and obtains the result shown in the table 1.1. So in the table 1.1, you should first fill in the blank spaces here, then this is done by 16.55 you subtract with 0.00 with the initial burette reading to form the titer 16.55. Then next 32.85 minus 16.55 16.30, 16.10 minus 0.10 16, 32.30 minus 16.10 16.20, and you should maintain 2 dp for all the burette readings that you get. Then for I, complete the table 1.1. I did so just now. Then calculate the mean titer. So to calculate the mean titer, you can only use the 2 closest non-rough titers of difference 0.1 centimeter cube or less. So in this case, we would choose 16.30 and 16.20 only. Then you find the average of them too. 16.3 plus 16.2 divided by 2 becomes 16.25 cm cube. And note that burette, this is the mean titer of the solution that is in the burette, which is NaOH in this case. Okay, next question for II. This is rather tricky one. So calculate the amount in mole of unreacted HCl in the solution prepared in step 7. So we know that the unreacted HCl actually reacts with NaOH in the titration reaction. So first, we need to get the mole of the unreacted HCl that reacts with the NaOH. So the formula for mole is N equals to C times V. So because the concentration we use is 1 mole per dm cube for NaOH, 1 mole dm cube of NaOH is used in the burette, and the NaOH to HCl has a ratio of 1 to 1. So the mole of NaOH is equal to the mole of the unreacted HCl. So mole of NaOH is calculated by this formula. Then you concentration is 1, volume is 16.25 cm cube, but you need to convert it to dm cube, so divide by 1000 is equal to 0.01625 moles for of unreacted HCl. But however, this is the transferred 25 cm cube of the HCl. So you want to find the mole of unreacted HCl in the solution prepared in step 7. The solution prepared in step 7 has a volume of 250 cm cube total. So you want to convert 25 cm cube to 250 cm cube. You could do it by 0.01625, you divide by 25 cm cube, you times 250 to form 0.1625, or because 25 cm cube to 250 cm cube is only times 10 cm cube times 10, you just 0.01625 moles times 10 become 0.1625. So there is final answer, HCl unreacted in the solution prepared in step 7, 0.1625 moles. Then III, calculate the amount in mole of CaCO3 that reacts with the excess of acid. Use your answer to calculate the percentage by mass of CaCO3 in the eggshell. Show your working. So first, you want to calculate the amount in mole of CaCO3. Then second is calculate the percentage by mass. So first question. So because in the previous question, we already get the value of moles of unreacted HCl in 250 cm cube. We just need to find the amount of HCl that actually reacts with the CaCO3. So in the previous question, the unreacted HCl is 0.1625 mole. Then we can find the initially added HCl is how much. So in the context that I used just now, 100 units of HCl. First is you add 100 units of HCl with CaCO3. The 100 units has a mole of this, 100 cm cube times 2 mole per dm cube HCl. So you want to find the mole is because mole is N is equal to volume times concentration. You just do 100 cm cube divided by 1000 to make it dm cube times the concentration is equal to 0.2 moles of HCl initially. The 100 units of HCl is equal to 0.2, okay, right now. Then 0.2 you would minus with the unreacted HCl, 0.1625, to form the reacted HCl with CaCO3, which is 0.0375. So this is your answer to the first question. Then let's go to the second question where it asks you to calculate the percentage by mass of CaCO3 in the eggshell. In order to do this percentage by mass, the mass of CaCO3 is divided by the mass of powdered eggshell used times 100. So because the mass of the powdered eggshell here in the beginning of the question is 2.136 grams, and so you need to find the mass of CaCO3 first. You already have the mole of HCl that reacts with CaCO3, and because CaCO3 to HCl is 1 to 2 ratio, you would divide 0.0375 by 2 to form the mole of CaCO3, 0.01875. Then moles is equal to mass over mR. So mass is equal to mole times mR. Here, mole times mR. The mR of CaCO3 is 100. 100 times 0.01875 is 1.875. Then 1.875 is divided by the previous number 2.136 times 100 to form 87.78 or 87.8% in 3 significant figures. However, in the answer key, the percentage by mass of CaCO3 is actually 87.9% if you use the MR 100.1. But in this case, I use a different Cambridge periodic table and got 100. So you should actually get 87.9%. So next is C. Name a suitable piece of apparatus which could be used to transfer 25 cm cube of solution in step 8. So step 8 is transfer the 25 cm cube from the 250 cm cube volumetric flask. In this case, you would use you put this in brackets, 25 cm cube volumetric pipette so that it could be precise. Next, D. In step 4, a conical flask is weighed using a balance accurate to 3 decimal places, and the mass is recorded. The eggshell is placed in the conical flask and mass increases by 2.136 grams. Calculate the percentage error in measuring the mass of the eggshell. So percentage error is actually uncertainty divided by the mass increase. Mass increase times 100, or uncertainty divided by the value times 100. So because I'm using a balance accurate to 3 dp, so 0.001. Usually for uncertainty, you actually divide the smallest accuracy by 2. You divide it by 2. This is the formula for every uncertainty. You divide it by 2. 0.001 divided by 2, you get 0.0005. And because you are measuring the initial mass of the container, then of the conical flask, then you're going to measure again the conical flask with the mass of the eggshell. Then you're gonna minus the masses. You're gonna be measuring it twice. Initial final minus initial measuring. So for every experiment, it's 0.001 divided by 2 becomes 0.005. And because you're going to be measuring twice, one with the conical flask and another with the conical flask plus eggshell mass, you need to multiply this 0.0005 times 2, because you're measuring it twice, initial measuring and final, to form again 0.001, and then 0.001, you put in the formula 0.001 divided by 2.136 times 100 is equal to this percentage, 0.0468%. In 3SF, 0.0468 is the percentage error. Then E, state the effect on the percentage by mass. This is different. Just now is percentage error. This time is percentage by mass. Percentage by mass is CaCO3 divided by mass of powdered eggshell used times 100. If the eggshell is not completely dried in step 2. If the eggshell is not completely dried, there's of course additional mass of water. So but then the mass of this water is presumed to be the mass of the eggshell. So there is a greater mass increase of the eggshell. A greater mass increase of the eggshell would lead to a lower percentage by mass. Lower percentage by mass of CaCO3. And that's the effect. Next, F. The student repeats the method using the same apparatus, but decides to use 0.1 mole dm³ of NaOH to reduce the risk of corrosion or damage to ice. Explain how this introduces a weakness to the experimental procedure. So for complete titration, when 0.1 mole per dm³, a lower concentration is used instead of 1 mole per dm³ for NaOH, you could see that C equals to 1 mole per dm³ is equal to, just now, volume of NaOH is 16.25 dm³. Then when C equals to 0.1 mole per dm³, how many is the V? There is no way that a lower concentration would lead to a higher volume. So because lower concentration of a substance means there is a lower rate of reaction, and so a predicted larger volume would be required. So when you divide by 10, 1 from concentration of 1 to 0.1, you divided it by 10. This one, the formula would be you multiply it by 10. If you use the mole way, concentration and volume, you find the mole, and then you use mole to find this volume, you would get volume equals to 162.5 dm³ instead of 1.625. Nah, so your answer would be a very large volume of NaOH in the burette is required at volume of 162.5 dm³. But then this is too large for the 50 cm³ burette. This is the weakness to the experimental procedure. So for the next question, number 2, it says it is possible to measure the rate at which potassium manganate VII KMNO, in which potassium manganate VII or 7, in which potassium manganate VII KMnO4 aqueous with an MR of 158, which we need to be noting down for later questions, diffuses through a permeable gel using the following method. So this is the Petri dish containing permeable gel, and this is the hole made in the gel. The hole will be filled with a sample of aqueous potassium manganate. And then step 1, a Petri dish is prepared with permeable gel. Step 2, a hole of diameter 0.5 centimeters is cut in the center of the permeable gel. Step 3, a sample of KMnO4 is placed into the hole, and at the same time a stopwatch is started. After 3 minutes, the diameter of the colored spot is measured and recorded. The diameter is measured every 3 minutes until there are 3 successive equal measurements. So this means that it is until it's measured every 3 minutes until the values are constant. So later you should identify that the time is actually the x variable, the diameter increases the y variable as seen in the graph here. So the first thing you have to do is A, plot the graph on the grid to show the relationship between the diameter increase of the colored spot and time, y against x axis. Use a cross to plot each data point and draw a line of best fit. Line of best fit doesn't necessarily mean straight line. It just means it could be a curve as long as it connects all the crosses. So here you can't actually see it, but I've actually plotted it like that here, and there's actually this outlier that I'm going to be instructed to circle later. Okay, so to draw the x, you can't actually draw it as big as 4 squares. You have to actually do it around that size. This is correct, this is wrong. It should be small enough. Okay, so later so in here like this, I will connect the graph like the one I did on paper, but it's quite difficult to do it right now, so just refer to the line that I have drawn. Then as you can see, it straightens out at the end. Okay, next, BI. On the graph, circle the point which you believe to be the most anomalous, or as the outlier, which is this one. When I was drawing the graph, that one was the most out of the line. II suggests a possible explanation for this anomaly. So the answer would be the diameter was measured too early, at less than 3-minute intervals. So as you can see in here, every interval is 3 minutes. But then there could be a human error where I accidentally measure at minute 5. This became an outlier like that. Okay, next question. C. Draw a suitable tangent to the line at time 15 minutes. Calculate the gradient of your tangent. State both sets of coordinates used in your calculation. The stated coordinates must be from your tangent. Give the gradient to 3 significant figures. Okay, so I need coordinates and gradient, and draw tangent at 15 minutes. So time 15 minutes, this one, time 15 minutes, you can draw a line up. So this point, I need to draw a tangent at that point. Then I not only have to draw the straight line at minute 15, but I also have to draw a triangle, as you can see here. Then a triangle that is about larger than 50% of the curve. I also have to draw a triangle. Then I'm going to take the corner coordinates, this one and this one. Then I got coordinates of tangent 4, 1.3 and 33.5, 3.6. Then I inserted here and I calculated the gradient. The gradient formula is m equals to y2 minus y1 over x2 minus x1. So m is equals to 3.6 minus 1.3, 23.5 minus 4, then you divide it, is equal to 0.1179, then 3 significant, rounded off to 0.118 cm per minute. Next number, D. Select appropriate data from table 2.1 and calculate the average rate of diffusion of KMnO4 in centimeter per minute. So the average rate of diffusion would be the point where the diameter increase would be stagnant, constant. In here you could see that it's 3.66. In the graph you can also see it's where it plateaus. It starts to be 3.6 centimeters at minute 30. So in order to calculate the average rate of diffusion of KMnO4, you divide the total diameter increase during the time given. So total diameter increase up to the maximum is 3.6. So it reaches 3.6 diameter increase during 30 minutes span. So 3.6 divided by 30 minutes becomes 0.12. So 0.12 centimeter per minute is the rate of diffusion of KMnO4. Identify the independent variable in this experiment, which is the variable that you change in order to get the values, is time. Suggest how the experiment could be made to be more reliable. It states suggests how the experiment. It doesn't state suggests other ways. That's a mistake of mine. I actually initially suggested other ways in order to make the experiments more reliable by adding new variables. However, I'm not supposed to do that in this case. You're just supposed to say repeat the experiment to show that the points that you got in the first trial is the same as the points you're going to get in the second and third trials. So it shows that the points are reliable. So G, another compound of potassium which is colored is potassium dichromate, K2Cr2O7. So just now we used KMnO4, this time it's K2Cr2O7 with an MR of 294. And just now we read that the MR of KMnO4 is actually 158. And here I've written 158, K2Cr2 at an MR of 294. This compound is corrosive when aqueous. It is possible to use the method described earlier to determine the rate of diffusion of K2Cr2O7. I. Predict how the graph obtained for K2Cr2O7 would differ from that obtained for KMnO4. So, because K2Cr2O7 has a higher MR than KMnO4, it has a slower rate of diffusion because technically you could say higher mass, it's heavier to move, heavier to diffuse. So you could say slower rate of diffusion. So there is a less steep gradient. Yeah, okay. Then II, apart from temperature, state one variable which must be controlled when comparing the rate of diffusion of K2Cr2O7 and KMnO4. So it would be the concentration of K2Cr2O7 or KMnO4 solution. Because, for example, there's a higher concentration of KMnO4 than the one shown in this experiment, and so there would be a greater rate of diffusion. So concentration is definitely one variable that you should be keeping constant because it affects the rate of diffusion. HI. Other than wearing eye protection, state one safety precaution that the student should take if they were to use potassium dichromate, which is, just now it says corrosive when aqueous. So I stated that we should use safety gloves, but the answer key actually stated that we should use chemically resistant gloves. So you could answer either one of the two. Another student suggests that to compare the rate of diffusion of K2Cr2O7 and KMnO4, it would be easier to place solid crystals of each of these compounds into the holes in two petri dishes of permeable gel. In this experiment, we actually used the aqueous form of K2Cr2O7 and KMnO4, but then the student suggests that we should use solid crystals instead. So solid crystals is obviously going to be more difficult to diffuse into the permeable gel because it's in solid form rather than aqueous. So it's also because there is a lower surface area with solid crystals, so you could say it affects the rate of diffusion. And another would be size of crystals are not uniform, and so it could affect the surface area. It could affect the rate of diffusion eventually also. So another practical problem that this would cause would be insolubility. Solid crystals may not dissolve into the gel and would affect the experiment all in all. Okay, and that's it for this paper. Thank you.